Welcome to the lecture on deep reinforcement learning in artificial neural networks. My name is Johanni Brea and I am excited to have the opportunity to walk you through some recent advances and applications of deep reinforcement learning. In this lecture, we will look at applications in the domain of video games like the Atari games or the Doom environment. We will also look at simulated robotics like the humanoid that tries to walk or the half cheetah. And we will look at applications to board games like chess, shogi or Go. In video games and board games, deep reinforcement learning methods reached superhuman performance during the last 5 years. Very broadly, deep reinforcement learning methods can be divided or classified into model-free and model-based methods. Among the model-free methods, we can further subdivide into policy optimization methods, of which you know already policy gradient, and Q-learning, of which you know already deep Q networks. Among the model-based deep reinforcement learning methods, we can distinguish those that are given explicitly a model of the environment and those that learn the model of the environment. In this lecture, we will briefly discuss all the methods that are highlighted in light red here. References to those methods and the other methods on this slide can be found on the references slide at the end of this presentation. This lecture is divided in 3 parts. We will first discuss mini-batches in on and off policy deep reinforcement learning. Then we will move on to deep reinforcement learning for continuous control, and at the end discuss model-based deep reinforcement learning. In this video, we will now continue with mini-batches in on and off policy deep reinforcement learning. Usually, we train deep neural networks with independent and identically distributed IID mini-batches of training data. This is what you have learned, for example, for image classification. Now, in this section, you will learn that we should not form mini-batches from sequentially acquired data in reinforcement learning, but rather use a replay buffer from which one can sample IID or run multiple actors in parallel. In reinforcement learning, subsequent images are typically highly correlated, as you can see in this example of the Atari game Breakout. If we look at subsequent images, the ball is roughly at similar positions, and the blocks, the colored blocks in the middle here, they're still roughly at the same position. However, images at the end of the episode may look quite differently from those at the beginning of the episode. Now, this is really in contrast to what we typically see in image classification settings, where we shuffle the training data to have approximately independent and identically distributed mini-batches. Why is this important? Why should we have IID mini-batches? Let me illustrate this with a simple example. I look at the single weight in a deep neural network here. The weight changes are temporally correlated. At the beginning of an episode, the weight changes here are mostly negative, whereas towards the end of this episode, the weight changes are mostly positive. If we now run simple gradient ascent, where the weights are just the weights at a given time are the weights at the previous time step plus some learning rate times the weight changes that you see here, then the weight will move to quite large negative weights and afterwards again up. So these temporally correlated weight updates can cause over time large weight changes. Now what happens if we take this data here, the correlated, temporally correlated data, and reshuffle it in time? The blue data points here are exactly the same data points as the red ones, but they are reshuffled in time. Now there are as many positive as negative examples at any moment in time, at any moment in the episode. If we run gradient ascent on the blue points, we get this trajectory of the weight and no strong deviation to large negative weights. Now, if you imagine that the policy of an agent actually depends on the weights of the neural network, then you can imagine that large deviations in weights can lead potentially to unstable learning, whereas the reshuffling of the weight updates in time stabilizes learning. To understand how deep reinforcement learning methods can deal with the temporally correlated data, I need to remind you of the difference between on and off policy methods. On policy methods, like policy gradient or SARSA, attempt to improve the policy that is used to actually make the decisions. Whereas off policy methods, like Q-learning, improve a policy that is different from the one that is used to generate the data. For example, in Q-learning, we may use epsilon-greedy exploration to generate the data, but then the policy that is actually improved is the greedy policy. Now, for off-policy methods, there is a pretty simple solution to this problem of correlated data. In off-policy deep reinforcement learning, for example, in deep Q networks, one can just put many, for example, 1 million experiences of observations, actions, and rewards, single steps, of a single agent into a replay buffer. This buffer is nothing else but a first in, first out memory buffer. And then we can just randomly sample from the replay buffer to obtain mini batches for training. The random sampling procedure would lead to something like the blue reshuffled data that I've shown you in the example of the previous slide. Unfortunately, we cannot use replay buffers with on-policy methods. The reason is that the experiences in the replay buffer would be obtained with an old policy and not the one that is actually currently used to make decisions. This is because after we update the policy, the replay buffer no longer contains the actions that would be taken by the policy, by the updated policy. Therefore, an alternative solution is required for on-policy methods. The proposed solution for policy gradient or advantage actor-critic methods like A2C is to run multiple agents, for example 16, and environment simulations with different random seeds in parallel. Ideally, such that every agent sees a different observation at any moment in time and is at a different part of the episode. Like this, the multiple agents, the observations and actions and rewards of the multiple agents are not correlated with each other, and we can obtain mini batches from the observations, actions, and rewards of the multiple actors. Let me briefly summarize the structure of the deep Q network of DQN algorithm in this pseudocode. It really is one of the templates of deep reinforcement learning nowadays, and many methods build on that template. So in deep Q networks, we initialize the neural network Q theta that takes states, for example, Atari game images as input, and produces in the output layer the Q values for the different actions. And we initialize also an empty replay buffer R. Then we set the target network to the current Q network and initialize the counter and observe the first state. You may want to go back to the lecture from last week to understand why we use this target network. Now we repeat until some termination criterion is met the following steps. The agent takes an action, for example with epsilon greedy exploration, and observes a reward RT and the next state ST plus 1. Now this state, action, reward and next state are put into a replay buffer. From time to time, now the training procedure of DQN samples a random mini-batch of the transitions Sj, Aj, Rj and Sj plus 1 from this replay buffer. It's important that these J's here are not from adjacent time points, but really at random points in this replay buffer. Now to update the weights of the Q network, one takes now the gradient over this difference between the current reward and the Q value for the next state of the target network minus the Q value for the current state action pair, and averages across the mini batch. Then we just increment T and reset the target network from time to time. The algorithm in the end returns the Q network. Let me also summarize the advantage Actor-Critic architecture in this pseudocode. Actually, you may have heard of A3C. The 3 here comes from an algorithm that was proposed by researchers at DeepMind, and it was actually called asynchronous advantage Actor-Critic. But it turned out that asynchronously running the different workers is not really a requirement, and nowadays it is more common to use A2C, the advantage Actor-Critic, that runs the different actors in parallel. Okay, so the advantage Actor-Critic method works like this. You initialize the policy neural network pi theta and the value network v phi, set the counter to 0 and observe the first state. Now, for all workers, for example, these 16 workers, one takes an action AK in the environment, observes reward and the next state. Now, each worker computes the expected future discounted reward, the reward plus gamma times the value function, and the advantage, which is simply the expected future discounted reward minus the value of the current state. Next, the learning procedure of the advantage Actor-Critic method receives all the advantages and actions and states from the different workers and updates the parameters of the policy network with a gradient from this advantage loss across the mini batch. Similarly, the value network parameters phi are updated by just making it closer to the actual future discounted reward. Then we increment T, run this all until some termination criterion is met, and return the policy network and the value network. So what are the advantages and disadvantages of on and off policy deep reinforcement learning? Off policy deep reinforcement learning typically tends to have lower sample complexity. What we mean by sample complexity is that the reinforcement learning agent needs fewer interactions with the environment to come up with a good policy. The reason is that the replay buffer with, for example, 1 million experiences can be used many times to improve the neural network. So this is why we may end up with fewer interactions with the environment. In contrast, in on-policy deep reinforcement learning, we cannot use the old experiences, but always use on the current experiences of the k different actors. Now, an obvious downside of off-policy deep reinforcement learning with this huge replay buffer is that it may require higher memory complexity, because we need to store all these many experiences in the replay buffer. Whereas on-policy methods obviously have lower memory requirements. Let us conclude this section with a quiz. If we use the Sarsa loss Rj plus the Q value of the next state action pair minus the current Q value in the DQN algorithm, we just need to include also the next action Aj plus 1 in the replay buffer and everything will work. Is this correct or not? This is not correct. The problem is that Sarsa is an on-policy method, not an off-policy method, and replay buffers can only be used with off-policy methods, because the action Aj that is stored in the replay buffer may not anymore be the one that would be chosen by the policy after having changed some of the parameters. We could use multiple actors instead of a replay memory with Q-learning. Is this correct or not? This is correct. We could use indeed multiple actors instead of a replay memory with Q-learning. However, a replay memory is typically more sample efficient than using multiple actors in parallel. But nothing hinders us from using Q-learning with the type of method that is used in A2C. In A2C, if all parallel workers K start together in the first step of the episode and every episode has the same length, we do not get the desired effect of IID mini-batches. Is this correct or not? It is correct, at least to some degree. We may still get somewhat different observations from the K different workers, but if they're all in sync, always start together at the beginning of the episode and always end together at the end of the episode, then we will not get this nice reshuffling that we see, that we would get if they're really out of sync, if the episodes have different lengths or the actors start at different positions in the episode.